Welcome and thanks for attending today's Ask CTE Contributors webinar event. I'm Dennis Faith, the owner and publisher of Cutting Tool Engineering, and I'll be serving as your host and moderator for this 1-hour webinar focusing on products and strategies recommended for deep hole micro drilling. Before I turn things over to our presenters, I just want to remind everyone that today's webinar is intended as an extension of the article that was published in this month's issue of Cutting Tool Engineering. The article, titled Tiny Drillers, discusses how properly designed and applied tools make deep hole micro drilling less treacherous. Today's representatives from Kennametal, Sandvik, and will delve deeper into the products and strategies recommended for deep hole micro drilling. In addition, a representative from MAQAB will discuss that company's 8mm diameter vibration damp turning tool, which was the subject of the sidebar in our August issue with this main feature. So with that, I'm going to just introduce our speakers. Joining me today is Frank Martin, the Hole-Making Global Product Manager for Kennametal Inc. Jeffrey Washburn, Product Specialist for Solid Carbide with Sandvik Cormont Company, and Shalene Fu, the Chief Technology Officer for Swedish toolmaker MAQAB. So let's begin by turning things over to Frank.
So thank you very much for having us, and thank you for having this opportunity talking about micro drilling. We have different speakers talking about different aspects of micro drilling. I really appreciate it. And then we will talk a little bit about some key features or aspects of micro drilling to help you guys out there to run the jobs and make reliable and fairly good holes of good quality in your workpieces. Kennametal has just launched in April a product line called KenDrill Micro, which is a completely new product line in addition to us, and it carries some key features that we want to talk about that really enables the drill to make these small holes in a reliable way. One of the key feature is the special coolant hole geometry that we are applying. Drills with solid carbide drills with through coolant channels usually have round channels, and these channels, do not use the full space that you would have in a carbide body of a drill. So, changing the shape of from round to triangular holes actually is helping a lot to increase the coolant flow through the tool. And on a later slide, I will show you what effect that does have. The other thing that I want to show you on that slide here is the special web thinning and the gashing that you will see. It's a theory that, in drilling, the cutting speed in the center is 0. On the outside, it's maximum. So actually in the center of the drilling, you're actually just pushing the material aside. And the earlier you are able to create a chip and get the tool into a cutting mode, the better it is. And with this special gashing, we are able to curl a very short chip and to help to separate the chips from each other. And chip evacuation is the other key to make a micro drill work. So how does that look like in a comparison? We have done a lot of tests, in our labs to compare conventional tool design with round channels and to compare them to coolant channels with a triangular shape. And what you actually can see here, I hope it is a little bit visible because it's a little movie you're running. You can see that the flow velocity is marked by the color. And the higher the velocity is, the higher the coolant volume you're getting through. So when you compare a regular round channel with a triangular channel, you will see that the coolant flow rate is 3.7 times higher compared to a round channel. So what does that mean? Actually, it means that you are able to apply this tool in other conditions. So for example, in difficult conditions. So what you can see on that screen here is what the effect is if you have a higher coolant volume flow. So you see multiple graphs here. So the regular graph here is a graph with 70 bar coolant pressure or 1000 psi. You know, the dotted line is with 290 psi. And now you can see the comparison between round channels and triangular channels. Actually, the effect is that with the triangular channel and 290 psi, you are actually able to provide nearly the same coolant flow compared to a round channel with 1000 psi. So what does that mean? That actually means you can apply this tool on weaker machines where you don't even have high coolant pressure, or you can run your existing process with lower pressure. You can save energy and costs, and you have a better influence on your chip evacuation and on the cooling of the cutting edge. So increasing the volume of the coolant is really an important thing to do. Next slide. Okay, on this slide here, actually, I would also have some videos which compare what the effect is. If you run a 50 times D drill, like in this example, and you apply the coolant pressure, you will see how much volume is coming out of that, right? It's not much, but it's helping. When you compare that now to a triangular channel, you will see that with the same cutting conditions, you know, all the things are quite the same. Actually, the coolant that is coming out of the hole is much higher. That's much more volume. And that means you have better coolant, better chip formation, and better chip evacuation. So I hope I am able to switch the slides now. Oh yeah, it looks like this. And the other thing now, we're talking about the coolant channel and the design. So you try to get more volume through. The other thing, designing a deep hole drill for micro application is, you know, how can you keep the cutting forces on the lowest possible level? Because the higher the cutting forces are, the higher is the likelihood that the drill will break. So if you have a longer and longer and longer drill, you know, the drill gets weaker and weaker. So it's really key, and it's really an enabler. When you want to design extreme long drills, you need to have drills that create low cutting forces. And in our benchmark and lab test, the final outcome of our testing was that the cutting forces that we are creating with our gashing, you know, are the lowest. So compared to major suppliers in the market, we found that these are pretty low, and that is helping us to design very long drills. And how do we measure that? You know, think about how we measure this. I'm sorry, something's switching slowly. We have an entry point and we have an exit point, right? So what we are doing is we are measuring where is the entry point, is it accurate enough, and is the exit point as accurate as this. So this is just a dry chart that compares how the position accuracy is in a bar chart. But I find it much more interesting to see that dotted chart, because here you will see that you have the entry position in yellow, and you have the blue yellow position. The yellow circles are the exit sides, and the blue circles are the entry sides that we have just seen on the other slides. And we are trying to measure how far the exit side is away from the center and the entry point. And we found that even with extreme long drills, the whole position accuracy can increase a lot if you reduce the cutting forces. And this can be achieved if you are reducing if you are improving the gashing in the center to curl, you know, easy and short chips. Here in this application, I would like to share an example where we have, which is quite a typical example in micromachining. It's a bone screw, you know, from the medical application, actually a customer in Brazil. And you can imagine it's a very long and tiny screw. So the run out in this application must be extremely precise, because you should not deviate from the center, right? And the customer currently had problems to keep that run out as short as possible. So he was using a very complicated process. Now with our tools that create pretty low cutting forces, we were able to overtake this application simply because it was possible to run this with a one-shot application. Just a quick pilot hole, and then without any packing cycles, running through with an extreme long drill and keeping the run out as low as possible. The example is made with a 1.7 millimeter diameter drill with through coolant. And actually, my nearly getting towards the end of my little presentation, I would like to talk about coolant and the effect of coolant. When we talk about micromachining and flood coolant, it is really difficult. Whenever you have the choice between a full coolant drill and a non-coolant flood coolant drill, you should always take the full coolant drill. Because with the flood coolant, you are not even, reaching the bottom of the hole. So you're not really cooling the cutting zone. This is a little experiment that we did. We drilled a 1 millimeter hole into a plate, which was a 1/4 inch thick. And then we pushed, flood coolant on it. And then we put, a little box below and tried to measure how many drops are getting through. And guess what? Nearly nothing is getting through. Just by putting pressure, flood coolant on a hole does not mean that the coolant is really going through. And this was an empty hole. Now imagine there is a drill running with a helix, moving in the opposite position. So it really avoids that coolant is reaching the ground. But what we found was that when you simply compare non-coolant and the full coolant drill in the same application, that the tool life is dropping to half or even less, just because you are not, cooling the cutting zone and the cutting edge. Actually, you are just cooling the chip and the tool if you are doing packing cycles. So that's an interesting aspect that should always be considered. Of course, in some sizes, through coolant is not available, and flood coolant is the only option. And then you are good to go. But whenever you have the choice, you better take through coolant. Kennametal used to have some small drills in the portfolio before our famous Go drill. We used to have 12 times D drill and extreme long drills, and we have completed our offering now with this, yellow area here, starting from 1 millimeter going up to 50 times D, all with through coolant. And all these tools have the same features with the triangle shapes, with the special gashing, and with the special coating. So the program that we are offering is quite complete now, starting from 2 to 7 times D with pilot drills and going up to 50 times D. You can use this 2 times D or 7 times D drill as a pilot tool, and then you follow with the other ones. So point angles are adjusted to each other so that they are all work together as sister tools. So that would be it. I would be available for questions towards the end. So back to Dennis or the next speaker. Thank you very much.
Thanks, Frank. I'm going to turn things directly over to Jeffrey Washburn.
Okay, very good. Thank you, and thank you for inviting us, Dennis. We appreciate our relationship with Cutting Tool Engineering, and I think you guys are the gold standard for the cutting tool industry. So we appreciate the relationship. I'm just going to start out by talking a bit about the Sandvik offer in micro tools. I'll go through that pretty quickly, and then we'll talk specifically about a few application tips and tricks that may be a benefit to you all. Okay, so first I'll talk about what we call our 462 offer. It is the micro tools in the range of 0.03 millimeters up to 3 millimeters with a diameter ratio of 6:1 and external coolant only. As Frank mentioned, inevitably in micro drilling, there's going to be points when or applications where internal coolant is just not an option. So, so that's why this offer exists. And we always publish what we believe the hole tolerance is for the drill. We don't publish the manufacturing tolerance. So this product offer is what's called a JS7 tolerance with plus or minus 6 microns. And they come coated and uncoated. And then we have 862 or an optimized offer. It's just a more highly engineered product. The diameter range is 12 thousandths to 3 millimeter again. Depth to diameter ratio up to 80 times D. Internal coolant on most, but not all of this offer. Some of the very long tools don't have coolant through. JS7 tolerance again for most. And we can also offer customized versions of this line. So here's what we mean by optimized, like Frank was talking about. We have a very thin point to keep cutting pressure down. We have on the right here, you can see can you see my pointer?
Yes, I can.
Okay, so we have a reduction in diameter. That's to help coolant get down to the cutting edge. The diameter reduction is about 3% less than the cutting diameter. We also have a variety of helix angles on the tool to aid in chip evacuation. And then we have a polished T-land to help promote even wear. Okay, now let's just talk about a few tips about the setup for running micro tools. We like up here, and we like to see the run out at the shank to be about 5 micron, or about 2/10. You know, anything more than that at the shank, and you'll be fighting tool life and drill performance. Down at the tip of the tool, depends on the diameter, but let's just take a 1 millimeter example. We'd like to see 10 microns. If you're using external coolant, you want to make sure that you have it pointed in the best direction to aid the tool. And we like to see about 60 bar coolant pressure, although that's not always doable. That would be our recommendation. And then just briefly about tool holders. Tool holders with low run out are required for micro drilling. I'm not going to go into the spiel about our hydraulic tool holders, but just to say you have to use a performance tool holder. There's a lot of good holders on the market, but there's also a lot of bad ones. And you will be fighting performance again from start to finish if you don't have a high performance tool holder. And also just to mention here, Sandvik is a partners with a company called WTO. They make these coolant, spindle speeders that's driven by coolant, and RPM is absolutely key to optimizing micro drilling, especially deep hole drilling applications. You know, to get to 50 surface feet with a 0.5 millimeter tool, I think you need it's like 15,000 RPM, somewhere in that area. So a spindle speeder can be very beneficial for optimizing. And then a deep hole drilling strategy. We like to recommend a pilot hole, of course, to get a good start hole. 2 times D is a good starting place, not required, but that's kind of a good best practice. And then after the pilot hole is created with your long drill, you want to move the drill into the hole without the coolant on. The coolant pressure alone can snap these very small coolant through drills. So you'll leave the coolant off, move at very low RPM. We recommend 500 RPM and only maybe 12, 15 inches a minute to get into the hole. then turn the coolant on, and then start your feed rate. This of course is a no pecking cycle. And then it also recommends slowing down the RPM when backing out, and then shutting the coolant off before you exit the part for the same reason as the entrance. Just a good general best practice for cooling through drills. Just a couple little bullets about pilot holes. You know, Frank mentioned, you know, we want the point angle of the pilot cannot be less than the pilot hole on that point angle for your drill. That's kind of a given, but we just want to point that out. You can see in the middle there what can happen if you have a point angle that's not steep enough. And then diameter. You want the diameter to be very close to the diameter of the drill. This can put excessive wear and start out a hole not being straight. And then pecking. Invariably, there'll be pecking operations with deep hole drilling. You don't have coolant through for your tool, or whatever the situation might be. So here's some pecking strategies. We say, you know, not to extract the tool beyond the top of the part. Leave the point of the drill in the part so that you don't, you know, you have excessive contact with the outside of the part. It could cause hole quality problems and tool life problems. We do try to help optimize the pecking cycle. This can be a recommended starting values where the S equals 1 times D, but depending on the chip formation from materials, you may have to reduce that, or you may actually have the opportunity to increase that if you're trying to optimize cycle time. We have some software that we can give you that helps to optimize pecking cycles. In this example here, it's showing a case where if you're trying to optimize cycle time, you may not want to peck at 1 diameter deep per peck. So at the top of the hole, you may get away with some deeper pecking, and then as you get down near the bottom, you may need to reduce the pecking in order to control the chip evacuation. This is just a screenshot of the software we can give you. On the left here, this is the different definitions. We'll give you the definitions of all these values. You can plug in your values that you determined from our guide, and then this will write the G code for you. The normal G97 is not a good option for pecking if you're trying to optimize an operation. Uh-oh. Forgive me for 1 minute. Okay, enough on pecking. Sandvik offers micro PCD tools. That's kind of a unique product for us. These are some of the materials that are compatible with polycrystalline diamond. Beryllium copper is a very common one. Titanium, aluminum, high temperature plastic, glass filled plastics, ceramics, platinum is a common one as well. PCD can be as much as 100 times the wear resistance of carbide. That doesn't always transfer to 100 times tool life. 50 times might be a good guideline, and of course there's even cases where it's simply 10 times. But it can be a very economical way to produce high volumes of holes. And in the micro tool, PCD micro tools, we can do drills, reamers, end mills, ball nose tools and micro boring tools as well. Here's just a couple examples of this on the left here is a small face grooving tool. So this is a PCD cutting edge on a boring bar tool to produce a small face groove. And here's a small ID form tool, a little over 0.5 millimeter wide. These are all, of course, built to order. Another example of a spherical ball with a diamond cutting edge, just over 0.5 millimeter as well. There's just one specific example of a diamond drill, drilling alumina ceramic. This 1.7 millimeter diameter. There's the cutting data, no pecking, and we were able to accomplish 930 holes. And here's a couple images of the drills in the process. You know, a carbide drill probably have a tough time getting 10, 15 holes in this material. So that's just my my presentation. I have more examples of real world cases of deep hole drilling and with micro tools. If anybody wants to see, we can take a look at some of those specifics.
Okay.
If anybody's interested. And so there you go, Dennis.
Thanks, Frank. Thanks, Jeffrey. I'm going to go ahead and turn over controls to Chalene.
Thanks, Dennis, and thanks offering us the opportunity to present our company. My name is Chalene, and I work as the CTO for the company MEQ in Sweden, and I'm also one of the founders for this company. So before we go to any of the technical, let's spend a few minutes to introduce who we are. MEQ has been a spin-off company from KTH, the Royal Institute of Technology in Sweden, and was founded in 2016. We were founded by a group of researchers who are dedicated to the vibration problems in machining process. So we are very focused on developing solutions to handle the vibrations in machining. We sold our first product in 2018, and so far today we have sold roughly 5,000 units around the world. The products we sell, they are also available on MSC Direct in the US. And for some of you who haven't seen our brands, you might have seen our product with the other market players, because we make private label products for multiple market players as of today. And we have a global distribution network with roughly 50 plus distributors and covering all the major markets around the world. And so it's quite easy to access us if there's a need. And on the right hand side, I see a picture that actually represents the founders of MEQ. You can see the name of the company was actually from the 3 founders, and the other 2 persons are actually my professors when I did my PhD study in KTH in Sweden. So that's who we are. Now let's spend a few minutes to talk about what actually creates the vibrations in machining. On the right hand side of the slide, you will see a small animation where it shows when a cutting edge gets engaged with the workpiece, and any sort of disturbance during the machining process will excite the vibration motions on the cutting tool structure at its resonance frequency. And this motion of the tool at its resonance frequency, together with the cutting speed, will leave, together with the rotation speed of the workpiece, will leave some surface marks on the surface of the workpiece. And so together with the rotation speed, the features on the surface actually tries to excite the tool at its resonance frequency. And this is actually the root cause of the vibrations in machining, and it's a interaction between the machining process and the machine tool structure. And as all of us who are familiar with the mechanical design is that if you have a system where you try to excite your mechanical structure at its resonance frequency, it's a very easy way to start with a disaster in the engineering design. And so far on the market, so say in the engineering design domain, the most effective solution as of today to reduce the vibrations in machining is to provide a mass damper on a cutting tool structure. That means you put a mass install a mass damper onto the cutting tool structure to transfer the vibration energy from the cutting tool towards the mass. So the mass vibrates violently during the machining process, and the tool is kept stable. The mass dampers are actually not something new on the market. The first generation came in the 1930s and has been about 100 years up to today. In the first generation, the designer had been trying to use the fiber disc on the same material as on clutches on the vehicles to compress a heavy mass and use that to fine-tune the supporting stiffness of the mass. So this is the first tuned mass damper that we can find on cutting tools. And in the second generation, it was in the 1960s where the rubber becomes to be a commercially available material, widely accessible around the world. And then the people started the designers started to use rubber rings to compress the mass or support the mass. And the advantage is, of course, that the rubbers, if you compress and decompress, they can more or less go back to its original shape, so that you have a better controllability on the fine adjustment for the supporting stiffness of the mass dampers. And in the 1970s, then the designer came up with a new idea where they moved this tuning mechanism from inside the tool body to the external of the tool body, so that you can settle the tool into the machine, and then you can fine adjust the tuning of the mass damper. And in the same period, in the 70s, last century, then we have the most, so to say, widely deployed solution as of today on the market is that, again, we use, people have been using the rubber material to support the mass. And then the difference is that they have started to add the dampening oil into the structure to enhance the dampening a little bit. And if you look back to the history, I mean, the starting point to for a mass damper solution onto the cutting tool is that you have, as the step number one, is that you have to make a tuning for the mass damper. That means you fine tune the frequency of the mass damper to make a match to the frequency of your cutting tool, so that it works. If you are not tuned to the correct frequency, then it doesn't work. So this is the history. And when we did the research back in the days in the university, we see the challenge as of today is that if an operator in a workshop, if they get a bar on their hand and they try to install to the machine, and the challenge is that they wouldn't really know which vibration frequency this tool is gonna have in its vibration on. And here in the graph, I show a few examples where I compared a 25 millimeter, 12 millimeter, and also 8 millimeter product at different air body ratios from 6 times the diameter up to 10 times D, and you can see that the as the extension, so say, of the air body ratio goes on, the most prominent vibration frequency of the cutting tool actually starts to decrease. And the challenge is actually more critical when it comes to the smaller diameter product, for example, the 8 millimeter product or 5/16 in the inch. The issue is that all of a sudden, then the vibration frequencies changes quite much more compared to the other dimensions, because the diameter of the bar is small. So this was the challenge when we did the research, and we want to find a solution where we can address the vibration issue over a much better frequency range. And the real situation, not even to mention, is actually much more complex, because the actual vibration frequency of your tool or your machining system depends on multiple parameters, like if your machine bed is worn out, if it's new, or if even the operator who clamped the bar can make a quite a big difference in the vibration frequency. So this was the challenge we're looking at. And then we try to define the generations in the history, and we say that okay, the fourth generation was coming from the last century in the 70s, where we support we build the mass damper inside the cutting tool. We support the mass with rubber rings, and we put in the dampening oil inside to enhance the dampening. And in that solution, you can actually see that the rubber that has been used as the supporting material, it has actually quite a stable or constant elastic modulus or stiffness over the frequency range. And therefore, we come up with the new solution, and we classify it as the fifth generation, where in our solution, you can see that we don't have any viscose oil inside. It's purely a dry solution. And in this case, we have used special polymers to build these mass damper. These polymers, they have a nanostructure inside themselves, and they have a frequency-dependent stiffness. As you can see from the graph below, is that when the frequency increases, the green polymers in our product, their elastic modulus or stiffness will increase with the frequency to make a fine adjustment or tuning of the vibration frequency for your mass damper, so that it can match the frequency of your cutting tool. On the other hand, if your frequency of the vibrations in your machining system decreases, these polymers, they will get softer, so say to make a fine tuning of the vibration frequency on your mass damper to make them lower, so that you can have a lower frequency on the mass damper to make a match to your reduced vibration frequency in your machining system. And therefore, we are able to address the challenge for the 8mm tool, because if you remember 1 or 2 slides before, the smaller the diameter of the tool, the bigger is the change of the vibration frequency on the cutting tool structure. And in this case, 8mm really has the highest change in the vibration frequency, and therefore the traditional solutions actually have the limitations to address this application, and where we can really come up with a solution to produce, so to say, or create this 8mm product where it can actually works all the way from 5 times the diameter up to 10 times the diameter without any issue. And it's actually because the polymer inside can actually adjust itself to the vibration situations in your machining system. And to make this product more attractive or bring more value to the customer, what we did is that we also maintained to make sure that those products have a coolant through from the tool body, so that you can effectively cool down, so say, control the temperature in the cutting zone, and also to help to evacuate the chips in the machining process. And if we compare the 4th and 5th generation, remember that the 4th generation means that you use rubber ring to support the mass, and you put some dampening oil inside, which is also today the most widely used product on the market. And we compare with the 5th generation from MAQ, which means we use a polymer that can self-adjust its own stiffness or elastic modulus to make the fine tuning of the mass damper. We can see that if we compare the vibration amplitude measurements at different ambiguity ratios, and the x-axis represents the frequency and the y-axis represents the vibration amplitude, we can see that comparing to the 4th generation, the 5th generation from MAQ actually managed to reduce the vibration amplitude between 25% up to 45%. And that actually means the same product from MAQ actually has a much wider operation range compared to the previous prior art. And also the reduction of the vibration amplitude means that you could actually increase your productivity between 25% up to 45% if you choose the latest technology on the market. And if we put the tools between the 4th generation, the prior art, and the current invention we made at different ambiguity ratios, and if we keep the same machining conditions, we can see that when a prior art solution says that the product is actually defined for 7 times the application, it works quite okay at 6 times D without any issues. But at a 7 times D, we see that the fourth generation, the prior product starts to have issues on the surface finish. It can be acceptable as the finished product, but if you're the operator, you will always try to seek for better solution. And if you choose the solution from our product, you will see that you actually have a much wider operation range, covering all the time from 6 times the diameter up to 9 times the diameter without any issues. So this is the offering from the technology. It's really a simpler solution, but it actually provides much more function for the operators in the workshop. So today the product from the company actually covers the full range from 8 millimeter as standard up to 80 millimeter as a standard in stock. And of course, I mean, talking about the maximum aspect ratio on a cutting level 2 structure, we have maximum up to 15 times the diameter as the standard 2 solution on the market. And here is our contact information. We are new on the market, but we are growing fast. Thank you.
Thanks, Shalene. Appreciate it. I'm just going to turn the controls to myself. Okay. So while Jeff, while you were talking and presenting your, I guess I didn't turn my webcam on. While you were presenting your presentation, a few questions came in that were specifically intended for you, I believe. And it started with see, I guess a 0.30 millimeter drill. They're wondering what applications you would use for the drill that you were showing.
They're referring to the smallest end of the diameter range.
Yeah, I believe so. Yeah, is that the
question?
smallest?
Yeah, the applications for the very small, the 1.5 thou, 2 thou, those are very few and far between. And to be perfectly honest, I've never ran a drill that small. I haven't seen an application for those. We do a lot around 10 thou and up, but down in those very small tools, we rarely see applications for those. I'm sure they're out there. That's why the product exists, but it's not something I have experience with.
Okay, and there were a couple of follow-up questions to that. Did that come with the coolant through holes?
I'm sorry, we're breaking up there.
Yeah, seems like we're having a little bit of a freeze here, but does the same drill, does it come with the coolant holes?
Coolant holes from 1 millimeter and up, nothing under 1 millimeter.
Okay. And is there some device that you're using to measure the runout with that hole, with that drill?
Yeah, that's a good question. Once you get below, I'm going to say below 0.5 millimeter, maybe even below 1 millimeter, you should use some sort of non-contact measuring, either laser or comparator, any sort of dial indicator just really isn't feasible on those very small tools.
And do you have to do a pilot hole when you're using that one?
Yes, and anything deeper than 10 times D, you should use a pilot. It's not required at 10 times D. It's going to be good practice to use a pilot. Anything larger, deeper than 10 times D, but not required until, let's say, 15 times D.
Okay. Shalene, I wanted to direct a question that came in to you. Let's just make sure your microphone is, there you go. You were discussing holders for micro drilling and end mills. Or the holders for your turning tool. Do you have the same holders for end mills?
We are developing the rotating tool sector, and I can only really say an exact time when it's going to be released, but I can only say that we are really working hard in developing the rotational tool sector. Just come in a 9 anytime.
Okay, that's fine. All right, so with that, there were some questions that I'm going to double back to that some of our members of the audience asked that we address. One of them is, and this would be for anyone who wants to respond, recommendations for high-speed helical slotting and grooving about outer diameter on tubular shapes. Anybody have any recommendations for that?
That sounds like it's outside of my product knowledge.
And that's fine, and I'm just throwing it out there. If anyone does, and it's if not, we can pass and we can follow up with the individual who asked that question after the fact. But I just want to put it out there. So if that's
Rephrase it, please, Dennis. I didn't hear that correctly, probably.
Frank, I could barely hear you there for a second. Say again.
Yeah, can you repeat the question, please? I'm not sure if I fully understood the question.
The person's just asking for recommendations for high-speed helical slotting and grooving on outer diameter tubular shapes. And I'm not sure if that's directly related, but that's one of the questions that came in advance. So moving on to that. Okay. How do you reduce long chip evacuation and get longer tool life with these micro drills? Anyone?
Yeah.
I mean, you mean bird nesting or something?
I didn't hear.
Did you mean bird nesting of chips on the drill? Or?
Well, I guess, yeah, that would probably that, or, you know, if you want to call it long chip, getting rid of those chips out of there. It could be bird nesting, I suppose. I don't have all of the only question, the entirety of the question was just how do you reduce the long chip evacuation. But
you can drive that in many ways. You can drive that with cutting parameters or with certain strategies. For example, you can increase your coolant pressure if you are able to. That would certainly help. You can increase or reduce the speed, and you need to do it, in a controlled way together with the feed rate, so that feed and speed are in a certain relationship to really form a chip. Okay. So, and that's something you always try out. Every machine is different, every workpiece is different, coolant fluid might be different, and so on. So you start with your regular feeds and speed, and then you start to get control over it by increasing speeds and feeds or decreasing it, and then you check how the chips are looking like and how they behave. So if they're getting shorter, when you increase the speed, you might want to increase it even a little bit further until you've reached an optimum, and then it gets getting worse again. So this way, playing with coolant pressure, with speeds, and with feeds, that would be on a normal end, let's say. If you have enough time, for example, you can add packing cycles. But packing would always reduce your tool life, because packing always means that you hit the ground like on the first way, and that costs a lot of tool life. But packing, also interrupting of the drilling process, would help to make the chips shorter. And then you can, of course, also play with the packing cycles by just lifting it or moving the chip out, or the drill out, moving it certain ways out, back and forth. Jeffrey has shown us some strategies how to do that and how packing can be done. So packing is definitely, shorting your chips.
Good.
Apart from those comments, I mean, the feed and speed is always quite crucial, not only for drilling but also for turning as well, if you want to break the chips. And on top of that, if you talk about the breaking the chips in turning operation, then you really have to select the correct chip breaker on the cutting edge, and make sure that you consult a expert who knows about how to recommend the chip breaking. So say with your specified feed and speed and so on. On the other hand, if you look at the products we have designed, to remove the bird nest in a small holes, what we have done is that we designed a tool with two coolant exit. One is going to the insert, and the other one is going to the hole. And in some cases, if you have a blind hole structure, then it's actually recommended that you block the hole, that is you block the coolant to the cutting edge, so that you try to only use the other coolant exit to blow the coolant to the blind hole, and in that way to take the chips from inside out instead of outside from external to the inside. So this is quite important if you have a blind hole structure or machining.
Okay. Now there's another question that came in. It says, after drilling, when you retract a micro drill, should the drill rotation be kept on or off?
Very good question. We recommend reducing the RPM to maybe 500 RPM when retracting, although I have seen people successful at actually even reversing the RPM on retraction. The main thing is not to go too fast and make sure the coolant is off by the time you exit the hole.
I would fully agree.
If it's a long drill, yeah.
Yeah, reducing speed or even reverse, but don't keep it not moving. I've seen drills breaking just by pulling them out when they are not rotating. So yeah, definitely keep it turning, but not at the maximum speed, and even you consider to reverse it. For example, in soft materials, where it's very likely that the cutting edge could dig into the whole wall, that could always cause a break. So if you screw it out actually backwards, that could help to avoid that effect.
I can confirm that, because when I did assembly in my workshop back in the days, I drilled 50 small holes every day, and it was exactly the same method. You slow down a little and it goes slow when you get out. So thanks.
Thank you. Another question, and we are getting close to the 1 hour mark, but I want to try to get to the rest of these. What is, I guess, the benefits for corner chamfer instead of triangular coolant hole drills?
You need to compare apples with apples. A corner chamfer is a different thing. You try to achieve different things with a corner chamfer compared to the coolant channels. With the coolant channel design, you can play with your coolant volume and with your stability of the tool. With a corner chamfer, for example, a corner chamfer is typically when you machine cast iron, for example, and you have exit holes, you have typically a breakout on the exit side if you do not have a corner chamfer or a radius or something like that. On micro machining, it's not that critical, but a corner chamfer certainly helps to protect the cutting edge, because that can be a very sharp, outstanding piece of carbide. And to avoid breakouts and increase tool life in certain materials, a corner chamfer can help to boost that.
All right. Another question here that I'm not sure if I can read it here. It says, can you suggest cutting parameters for 0.03 millimeter drills?
Go to our website. Anyone's. I mean, it really depends on the tool, that you're using. Different manufacturers, different feeds and speeds. That's quite normal. They always try to sell their optimum, and you just look for it. I mean, that should be easy to find with Google search or something. Yeah.
You can also reach directly out to us, either one of us. I'm sure any one of us, for some specific application data that's needed. Be happy to help.
Sure. Yeah. Any of the individuals who want to will be able to reach you, and I'm going to put your contact information up in just a second. I just want to throw this one out there. I'm not exactly sure if I understand it correctly, the way it came in. 3 32nd diameter by 23 diameters deep in 6061. I believe they're just asking for recommendations for the drill that they might use for something like that.
I don't have those resources right in front of me, but I'm sure we can come very close. I'm sure
Yeah, we can.
And,
I can send you the information. We could have you follow up with the individual who asked that question. But yeah, I just throw it out there. I wasn't quite sure what they were asking.
Frank,
looking for a recommendation.
I'm sure Frank has an offer. I'm sure Frank has an offer as well.
Yeah, I didn't hear the diameter. It was probably an inch. Sorry, I'm a metric guy.
332nd diameter by 23 diameters deep.
Well, the LD ratio is not a problem. I guess the diameter, I have still difficulties for calculating from the top of my head.
A little over 2 millimeters. Little over.
Micro tools are typically below 3 millimeters, you know, and starting like Sandvik or some others from 1 millimeter on with through coolant, and below you will find tools without through coolant mainly. So, I mean, use your Google search, you will find something.
That's about 2.3 millimeters. So, yeah.
2.3. So that's easy to cover. Available from the shelf, even from Kennametal.
Yep.
Okay. So with that, I appreciate our contributors joining us today, taking the time and presenting your technical information. I also want to thank our audience for taking the time out of their workday and spending an hour with us. If anyone in the audience wants to reach out, like I said, here's some contact information on this screen. There's the email addresses, and I hope that's okay with you guys. I think we discussed this already, but they're email addresses, and as well, you could download in the handout section of your GoToWebinar control panel, you can download their presentations and the contact PDF that is sitting there. And if you don't get a chance to do that before we close out, the links will be available on our website to this information once the recorded version of this webinar is ready to go, which will take me about a day to get around to getting it posted. With that, I'm going to ask if our presenters have any last words. Also,
no, just thank you for attending, and I'd love to hear directly from any one of you.
Yeah, thanks a lot for the opportunity. Appreciate
it. Thanks, Dennis. Yeah, thanks to the audience. Yeah.
Thank you, Celine. Thank you, Frank, and thank you, Jeff. Really appreciate it. And with that, I'm going to go ahead and close the session. And again, thanks to everyone who attended.
Bye-bye.
Bye-bye.
Bye now. Yep.